invitation. It's a great pleasure to be here. So today I would like to talk about non-commutative Iwasawa theory, developed in the 5-author paper by Coates, Fukaya, Kato, Sujata, and Fenyako. So what does non-commutative mean in Iwasawa theory? It means that the Galois group involved they come from not necessarily abelian extension. So it took me some courage to put non-commutative in the title for a workshop that's on Hilbert's 12th, which is more abelian extensions. But my non-abelian extensions I'm going to consider, they're going to contain a certain abelian extension. And I will perhaps begin by reminding or introducing commutative Iwasawa theory and say why remind us why that's nice, and then move on to the setting. So I'll say a few words about the origin of Iwasawa theory. It goes back to the 19th century when Kumar was trying to solve Fermat's last theorem. So Fermat's last theorem says the following. Now a theorem says that the equation x to the n plus y to the n does not have integral solutions when n is And when you think about this problem, well, if n is a composite number, then you can write n is equal to g times h or something, and then n to x to the n is x to the g to the power h. So you only need to consider n is equal to 4 and odd primes. And when p is an odd prime, you can write the left-hand side also in a multiplicative form. So you can factorize it by taking a piece root of unity, going from 0 to p minus 1 is equal to z to the p. So Fermat's equation with exponent p can be rewritten in this multiplicative form, and now this is an element in z zeta p, which is the ring of integers of this field you get by adjoining a piece root of unity to Q. So multiplication or factorization in this ring becomes relevant. So here comes the concept of ideal class group, whose order measures the arithmetic complexity or how far away this ring is from being a unique factorization domain. So given a number field F, I'll write HF for the class number, which is the order of the ideal class group of F. And now I can state the partial result towards Fermat's last theorem due to Kumar. This is due to Kumar. 1850. He said if P is an odd prime, then first of all, if P doesn't divide the class number of Q adjoint zeta P, it's a primitive history of unity, then we have that this equation with exponent P does not have a integral solution. Okay, there's a second part. So how do we know if P divides the class number or not? This is computationally very difficult. If P gets at all large, if we didn't have the second part of Kuma's criterion, which is that if P divides the class number, if and only if the following holds. P divides the numerator of some odd zeta values, or negative zeta values, at least one of the following. Numerator of at least of zeta to the -1, zeta -3, zeta -5, up to zeta -b, where zeta is the Riemann zeta function. And so in particular, we have zeta of -1 is equal to -1 over, there's an expression for this in terms of Bernoulli numbers. Zeta of -3 is 1 over 120. Zeta of -5 is -1 over 252. And when you reach zeta of -11, you get like ones and -1s, one in the numerator, and then suddenly when you reach zeta of -11, you get the numerator 691 over 3276. I don't know this by heart. I just looked at before the talk. So you get the numerator. So by this criterion, well, that 691 divides the class number of Q adjoint zeta 691. So when you look at this, the first part of the theorem, you might think, oh, if P never divided the class number of Q in P, then Kuma would have solved Fermat's last theorem. Yeah, maybe it's a pity for Kuma, but this is precisely why number theory is interesting and beautiful, because it's precisely when P divides the class number, we see this relation between zeta values and class groups. And in Samit's talk, we already had this arrow going from zeta function to class groups. Your class group. And this, as he already mentioned, this relation was made, or we got a better understanding of this relation thanks to Ribbett. And Iwasawa theory is also a method of understanding this relation. And So given each prime number P, we have Iwasawa theory at P. And this also works as a bridge between these two sides. And it relates a p-adic analog of the left-hand side to the P primary part of the right-hand side. I'm not going to write zeta P because I already used zeta P for the primitive root of unity, but we have like a p-adic analog on the left-hand side. And in general, this idea can be generalized to L functions of, say, abelian varieties or H-Shapiro-Rich group on the right-hand side and P primary part. So the idea is to try to understand this relation at one prime at a time. And so Iwasawa's idea was the following. Oh. The Ribet's method, that also inspired Meza and Wiles in their proof of the main conjecture of Iwasawa theory, and this relation also inspired Iwasawa to develop the following idea, which is rather than looking at the class group of Q adjoint ZP, we look at the field view, how the arithmetic object grows in this tower of extensions you get by adjoining P power roots of unity. So you have Q and then you add Q zeta P and Q zeta P squared and to the n and up to, I'll just write zeta P infinity for the union of all these things. Then this is a P extensions. This is isomorphic to the units, Z mod P, Z unit. And so then you have, this leads to a more complicated arithmetic object than ideal class group of Q adjoint zeta P. But it has a nice natural action by the Galois group of this extension. More involved arithmetic object, which I'll introduce later. A natural action by the Galois group. We are adjoin zeta P infinity over Q, which is some cyclic group times gamma, where this delta is cyclic of order P minus 1. And gamma is isomorphic to ZP. There is a unique ZP extension of Q inside this extension, and that's called the cyclotomic ZP extension. So this is the unique ZP extension of Q contained in this extension. more generally, if F is a number field, you can get the cyclotomic ZP extension of F by taking the composite. Write F psych for the cyclotomic ZP extension of F. And we are going to consider non-abelian, well, not necessarily abelian, p-adic Lie extensions of F, which contains the cyclotomic ZP extension of F. So I'll write F infinity for a p-adic Lie extension, which means its Galois group is a p-adic, compact p-adic Lie group. And we are going to assume cyclotomic ZP extension is inside it. And so I'll write G for the Galois group of F infinity over F. And I'll write gamma for the Galois, the ZP extension F psych over F. And I'll write H for the subgroup F infinity over the cyclotomic F. And then, so the Iwasawa algebra is defined as the following completed group ring. E is lambda G is the completed group ring G over U, where U runs over open normal subgroups of G. And in the case F infinity is equal to the cyclotomic ZP extension, we know that this Iwasawa algebra of gamma is isomorphic canonically to the power series ring in one variable E and so we have nice structure theory for modules over this algebra, and that those are called Iwasawa algebra. So given a finitely, there is a structure theory for finitely generated lambda gamma modules. Finitely generated gamma modules. Structure theory for such modules is the following. The M is pseudo-isomorphic to some copies of lambda gamma plus some torsion paths from 1 to k and gamma divided by some elements of this Iwasawa algebra. And so it's like just like the structure theory for finitely generated abelian groups, we have some copies of Z and some copies of Z mod. And I, Z were some cyclic groups. And then, so by the Weierstrass stress preparation theorem, we can write this Fi in the following form. Fi, I'm going to always identify it as the power series ring. So Fit is equal to some powers of P times some distinguished polynomial, which is a polynomial. Its coefficients are divisible by P, and some unit in this algebra. So this is distinguished polynomial. You can reduce if you're just considering the ideal generative by just reduce it to a polynomial, sometimes some power of P. So that's very nice. And now I'm going to move on to the setting of elliptic curves, and I'll consider elliptic curves defined over a number field F.
This tilde is just pseudo-isomorphism, right?
Pseudo-isomorphism, yes. That P be a prime of good ordinary reduction for E. So we have to do the ordinary reduction of every prime lying above P in F. Then we have, well, again, I'm assuming F infinity is a PhD extension and it contains the cyclotomic B extension. And then I can consider the following Iwasawa module, which is this like more complicated arithmetic object that which turns out to be a finitely generated Iwasawa module. X E over F infinity. This is the contrarian dual of the P primary Selma group of E over F infinity. So maybe in the ideal class group scenario, maybe consider, imagine maybe taking the P Silos subgroup of the ideal class group in at the top and maybe taking the contrarian dual. So in the end, maybe we want to understand what's happening with the Selma group at the bottom field. So it's over F, not F infinity, but this has a nice, we understand the structure of this thing. And that's why we are doing it. This is the P primary Selma group of E over F infinity. And then this is finitely generated Iwasawa algebra, lambda G module. And in the case F infinity is equal to the cyclotomic ZT extension, we expect it to have really nice module theoretic properties. In addition to this, Mazur's conjecture. Feel free to questions and comments. Any comments? Case, we have the cyclotomic ZP extension. We have the following conjecture due to Mazur. Says if if E is defined over a number field and P is a prime of good ordinary reduction, then the Iwasawa module is a finitely generated torsion module. Then X P over the cyclotomic ZP extension. The finitely generated torsion lambda gamma module. And there has been progress of this conjecture. For example, Kato showed that this holds when E is defined over Q and F is a cyclic an abelian extension over. This is due to Kato. Oh. Secondly, if the Selma group over the base field F is finite, Mazur already showed this. And in view of the structure theory for lambda gamma modules, we can we can rewrite the Mazur's conjecture following way. So in view of the structure theory, Mazur's conjecture holds if and only if you quotient out this Iwasawa module by its P primary submodule, you get the finitely generated ZP module. This is bracket P means P primary submodule. And if Mason's conjecture holds for this module, then we don't have this copies of lambda gamma by the structure theory. So it's just pseudo isomorphic to some torsion modules. So if this holds,
I should have asked this earlier and you probably said it, but what is cell E over F?
this is the P primary Selma group of E over F. And that's over F infinity.
Okay.
Yeah, so really we want to understand this, but like we want to understand the P primary part of the ideal class group over F, but we are going up the tau and we are trying to study that and really get back to understanding this. So if this holds, we can define a characteristic ideal of this module. Which is just defined to be the ideal generated the product of the FIs. So if this would have been a finitely generated abelian group, this is just the order of the group, the product of the NIs, the order of the cyclic. And so this is the most important, this is an invariant that we care about in Iwasawa theory. So this is the characteristic ideal. And this is called the characteristic power series. Neatly determined up to a unit. Iwasawa algebra. Power series. And main conjecture of Iwasawa theory roughly says this is generated by a p-adic L function, which interpolates complex L values, and that's how we try to relate L values to Selma groups or arithmetic objects. But now the natural question is what if, one more invariant I want to define. The power of P in here is called the mu invariant of the Iwasawa module. Of this Iwasawa module. Yeah, so what if F infinity is not equal to the cyclotomic ZP extension? How does it, or does the arithmetic, or namely the Selma group of E over F infinity, does it relate in any way to the Selma group of E over the cyclotomic ZP extension if F infinity contains this cyclotomic ZP extension? In what way? To what extent? That's the arithmetic. F infinity relate to that over the cycle extension.
Do you define this Selmer of E over F infinity as the projective limit, the injective limit of Selmer of E over the finite?
Yes, exactly. Yes.
Yeah, no, I'm just confused about why points don't give an infinite part. I mean, are you saying that the Shop-Ravitch group is fine? Like, remark two, it seems confusing.
This is as in the case when this is finite, Maser can show this.
Oh, I thought you were saying that
We know.
in the case when it's finite. I understand what you're saying. I see.
So this means
I thought you were saying that this is finite, which was confusing.
Yeah, sorry.
that means the Mordell V is also finite. so-
Yes.
Yeah, but they can have an infinite part of the Selma group from the points on the elliptic curve. That's why I was confused about this.
Yeah.
Just not parsing the sentence correctly.
Yeah, sorry. Thank you for the question. Is it?
Yeah, I understand that. Yeah.
In the cyclotomic case, are there conjectures about this mu invariant? I mean, is there a mu equals 0 conjecture at some point?
Yes.
Yeah.
Yes.
But not in general.
Not, I mean, there is not always zero.
Not
but I think
always
There's
zero.
something in isogeny class that's supposed to be.
There exists an isogenous curve for which this is, yeah.
So, okay. So motivated by this observation, the 5 authors called Kato, Sujatha, and Fenyakov, they introduced the following category of modules. Kato, Sujatha, Fenyakov. Introduce the category MHG, curly AMHG, which are finitely generated lambda G modules, such that when you quotient out by the P primary submodule, you get a finitely generated Iwasawa module of H. Finitely generated lambda G modules. M, such that M mod MP primary submodule is a finitely generated lambda H module.
Who is H in relation to G?
H is the Galois group of F infinity over the cyclotomic extension. It's small. And they conjectured, and for these modules, they could formulate a non-commutative version of Iwasawa main conjecture. And they conjectured that the arithmetic objects we are interested in indeed lies in this category, and this is called MHG conjecture. MHT conjecture in 5. So in this setting, module xe over f infinity lies in this category MHG. There has been progress in this conjecture. Quite of well, the ones I could find, they seem to have some sort of mu equals 0 condition. So maybe mu equals 0 for the E over F cyclotomic ZP extension, or for some isogenous curve over some extension. And the idea was to see what we can do for in the case of over global function field. So I will move. I'll start. Now my F is going to be a global function field. While I'm writing, feel free to ask questions. Because this MHT conjecture, you can also define it, or state it in terms of abelian varieties and also over global function fields.
You don't know anything about the conjecture if the elliptic curve is defined over, or if the elliptic curve has like CM.
So TM is, yeah, it's better understood. So, but yeah, wait, in the number field setting, or
Yeah, number field setting, yeah. So like if the elliptic curve is defined over some extension over the current field, that's not abelian over Q, and then you take F infinity to be like the maximal P extension or P ramified, so that you have a cyclotomic and anti-cyclotomic tower. Do we know if this conjecture is true, or F infinity is the
I think you still need some mu equals 0 condition. Yeah. Because TM may be a natural extension to consider is the periodic Lie extension you get by meaning P power root of unity, and yeah, that case is quite well understood. In this over the number field setting, I hope I said that I was kind of assuming P is an odd prime, but from now on, yeah, P be any prime. I didn't say it. let F be our global function. A finite extension of rational function field in with finite constant coefficient field. And I'm going to assume that the characteristic of F is different from P. And in following the number field setting, I'm going to assume only consider following nice set of extensions. So again, you can define the cyclotomic ZP extension and so on for the this is the cyclotomic ZP extension of F you get by you take an algebraic closure of the constant field, and you get the P power roots of unity in this here, and then you adjoin it to F, and there's a ZP extension inside it. That's the cyclotomic ZP extension of F. And we define, we say periodic D extension F infinity is admissible if it satisfies the following properties. Admissible. One. Infinity contains the cyclotomic ZP extension. To the Galois group of F infinity F. This is a compact periodic Lie group, and we're going to assume this has no P torsion. Finally, we're going to assume that F infinity over F is unramified outside a finite set of primes. And then I can state a theorem, which is the following. That F be a, that A be a abelian variety defined over global function field F. Is whose characteristic, let P be a prime whose characteristic is different from F. infinity be an admissible periodic Lie extension of F? Then the MHD conjecture holds for the Selma group, the P-primary Selma group of A over F infinity. Dual of it, so X A over for the Iwasawa module X A over F infinity. The Selma group. Condition. It over the cyclotonic ZP extension, the mu invariant vanishes. Right. Yes. Yeah. So some remarks. So I want to make is that we are not the first people who started thinking about Iwasawa theory over global function fields. There have been many works in this direction. So we were in particular inspired by a PhD thesis of Seki, who studied this question for elliptic curves without complex multiplication of a global function field. So there is also work by Burns. There's also, for example, control theorem due to Fantini, Valentino. There's some work on P equals the characteristic setting due to you have also some
Not
not
in
not
this
but in
setting,
a commutative setting.
but
uh,
yeah, not in the setting of a billion prime.
But there is a non-commutative version of it due to Witte, who obtained similar results using completely different methods. But this theorem, it in particular tells us that Mazur's conjecture holds over in this setting for abelian varieties over global function fields. But I should emphasize that this is not true over number fields. So there are examples with non-zero mu invariant for number fields. To say something about the proof, I need to introduce some more definitions. So I'll write S for the non-empty finite set of primes, which includes the primes of path reduction for A over F and the primes which ramify in F infinity F. I'll write Fs for the maximum extension, which is unlimited of S. The S F infinity for the Galois group of F S over.
You want FS to be the maximum pro P extension, or you're just going for the whole thing?
I'm going for the whole. Given E in this set S, I'll write J. JV A over F infinity to be the direct limit over finite extensions of F contained in F infinity. And for primes W in L dividing E, I take H1 of L localized at B and A and take P primary part. Then I can fit the P primary Selma group we're interested in the following exact sequence. So the Selma group. Can be defined, it fits into this, it's the kernel. This optimization map going from H1 GS F infinity AP infinity to this product of the JVs. So roughly speaking, what we do is, so we want to show that this is a, finitely, this over it. The P primary component is a finitely generated lambda H module, but then it suffices to show that this, without taking the P primary, without taking the torsion, if we can show this is a finitely generated lambda h module, then that's enough. But in particular, looking at this short exact sequence, it suffices to show this for this bigger thing.
Have to take the duals first.
Yes, yes. So yes, thank you. Okay, then suffices to show. Again, by Nakayama's lemma. One, P infinity, the H co-invariant is a finitely generated set motion. Then there is a key input, which we can only show in the function field setting, which is that the P cohomological dimension of GS F psych is equal to 1. And then using this, you can consider the Hochschild spectral sequence involving H and G. This degenerates to reduce this question to showing something over this cycle abelian extension. Is a finitely generated P module. But then you can apply Nakayama's lemma again to reduce this question to something finite. You can show that the P torsion part is a finitely generated FP module, so it's finite. And this we can show by Kummer theory. So this is the idea. And so we could reduce a non-abelian question to abelian question. So I would like to end here. Thank you for your attention.
I think we have time for maybe very brief questions. Any questions for you, Yukako? Yes, Katrina?
So in your main theorem, your dual of the Salmon group, the XA over F infinity, that has a generalized mu invariant. Does that also vanish?
No, this we didn't draw. Yeah.
I think it should follow.
I mean, because if you know that the one over the cyclotomic extension vanishes, and if you look at your proof, you just work with the H1. I think both together should.
Sounds like a good thing to discuss afterwards. Okay, Christian, do you have a question?
The fact that the mu invariant vanishes here
Yes.
is probably due to the fact that this extension, the cyclotomic one that you are considering, is unramified.
Yes.
Yeah.
Yes.
So question here. So what if you take P equals the characteristic and you start with a real cyclotomic ZP extension, not the one generated by roots of unity, which don't exist.
No.
The one generated, say, by P torsion points of the cardinal.
Khalid's module. Yeah. Yeah.
There, the mu invariant may not vanish. And you can consider the same questions.
Right.
And
Yes.
Kummer theory is going to break down. There is no Kummer pairing
Yeah.
in that situation. Have you guys thought about that a little bit?
This is something I would like to definitely think about. Yeah, because we only have one ZP extension in the case we're considering, but in that case we have infinitely many geometric ZP extensions.
So, yeah, I mean, but there are ways of picking one.
Yes, the
Go
Khalid. Yeah.
I have some papers with Werner Bly that
Okay.
may,
Maybe you can send it to me.
may give you an idea.
Okay, thank you very much.
Any other questions? All right, so let's take 15 minutes and we'll start again with the last talk of the morning at noon.